Good morning, student. Today, I will take responsibility for do a lecture on crystal field theory. Second part. The first part we have talked about the octahedral complexes. Next, we have talk about tetrahedral complexes. I am Dr. Shubhendu Vishwas from Murshidabad College of Engineering. My privilege that crystal field theory is an important part of the different syllabus, the bachelor level, PG level, and the BTech student of current IIT, ISAR, and also current I'm delighted again explaining some of my views regarding this. Okay, let us start. When we have talked about the octahedral complexes, there are another views. When we are talking about tetrahedral complexes, is the structure and E and T2 confined. There was EG and T2. E and T, two electron that is facing in the cube and center of the edge of the cube. So three orbitals that is along in between the axis, along the axis that is in cube is the E, and the tetrahedral complexes you can find T, xz, yz, y, z square, z square, and the age of the complexes you can found T2, center of the edge of the cube is angle of 109 degree. And in the crystal field theory consideration is that the E orbital are taking the metal versus ligand complexes interaction, giving you 100 for one for EG is 109 minute 28 by 2 4 degree 44 minute, and also for T2G it is 35.1. So T2G is nearer to ligand and higher energy compared to the G. So instead of octahedral complexes, you can find there was T2G in the low in energy, he was in the upper position, whereas here interaction is very high, so the T2 is in the upper high energy and T in the low in energy. This degeneracy is lost given 3 is to 2. And if you compare to the octahedral complexes, the total data energy delta value is 4 by 9 the del 0. So there are 4 ligand in the octahedral complexes. Hence, crystal field theory roughly is the ligand field is roughly two-thirds octahedral complexes. Direction of the ligand in the octahedral complexes does not coincide with the d orbitals. That is why reduces the field by a factor of 2 by 3. Hence, delta t is roughly by 3 into 2 by 3 is 4 by 4 9 of octahedral field theory. As a result, all the tetrahedral complexes are high spin since the CFS is normally smaller than the pairing energy. Hence, Low spin configuration are rarely observed, and usually if a very strong field ligand is present, the square planar generation is favored. Here, trends of the delta T is that the delta T represents the octahedral complexes. It is vanadium chloride, the 409010 centimeter inverse, that is cobalt Cl4 minus is 3300, cobalt Br42 minus 39, cobalt iodine 43700, cobalt NCS is 4700. And if we consider the comparison as a crystal field theory from 0 to 10 number of electrons present in the d orbital, this M type of curve, this is for octahedral or tetrahedral. There is a considerable lower in energy, but pattern is same with the octahedral field. So you can find octahedral will be a shorter form of a tetrahedral CFSE, shorter form of octahedral CFSE compared to CFSE or L0. This is the structure of the uh, complex present in the tetrahedral field. Is the sample is given and see. Next, some of the example of the tetrahedral complexes giving you as the color of different metals present in the crystal, different color you can, lots of color or a variety and this final is used for CF. Final is given by mineral magnesium Al2O4, and there is a scientific name of CFC. How we can do it will be discussed the next topic of the circle theory. So we are in the wrap up season of the second part, that is tetrahedral complexes of the crystal field theory, their energy differences with the octahedral, why they are different and how much they are different we have discussed. So if you have any query, don't feel any hesitation, talk me in my email ID, find in the college website mcd.net, and I will be delighted in answering you. Thanks a lot. Thank you.